Hello. Now, this is the last lecture for the transducers course, and we are going to see again miscellaneous type of uh, sensors. In that, we first look at pressure measurements. The most popular um, method of pressure measurement is the diaphragm type. So there are two diaphragms called clamped diaphragm and corrugated diaphragm. Uh, the difference is the way that you make the diaphragm. So if you have let's say a tube, so if I look at this, the cutaway section here would be a circle. So if I have P1 here, P2 here, then the diaphragm will buckle like this for P1 greater than P2, or it will buckle like this when P1 is less than P2. Now if we take this as A and we choose a point R, right? I call this as point R from the center of the diaphragm. Then the displacement x can be derived as x suffix r is 3 by 6 into 1 minus mu square divided by 16 into a square minus r square whole square divided by e into t cube in the whole into P1 minus P2. Here mu is the Poisson's ratio, E is the Young's modulus, T is the thickness of the diaphragm that we have put. So this is constant, so the deflection is proportional to P1 minus P2. So this is a clamped diaphragm, the ends are clamped. In a corrugated diaphragm you have something like this. So you basically make the plate to move in, so you can get the movement as when P1 is greater than P2. The corrugation helps part of the thing move. So by just checking, measuring the movement, we can see that we measure P1 minus P2. So you should understand that every pressure sensor is measures with respect to a basic pressure, like a voltmeter measures only voltage difference between point P1 and P2. So depending upon P1 and P2, we have different types of pressure sensor. So if I have P1 and P2 is open to atmosphere, and this is what we measure, then this is called open port pressure sensor. We seal this to atmosphere, right? Again measure P2, then it's known as sealed port pressure sensor. Now we can make P1 equal to 0, absolute vacuum, and measure X. Then this is absolute pressure sensor. Then we put P1 and P2. This we have differential pressure sensor. We supply both P1 and P2, and it's also possible that I can make this as 1 atmosphere sealed, and X is less than 1 atmosphere, then we call this as vacuum pressure sensor. Uh, this principle is the same, the way that we put the P1 and P2 device. Again, the fluid that we use also makes different types of pressure sensor. If the fluid is a liquid, then we call it as a wet type of pressure sensor. If the fluid is a gas, we call it as a dry type of pressure sensor. Again, both P1 can be dry, which means this kind of pressure sensor can be used only on gases, or it could be wet, which means it can be used for gas as well as liquids, or it could be dry and wet. So one port has to be gas and the other port has to be can be liquid. So we have these three kinds of pressure sensors. The way we measure the pressure, the displacement of the diaphragm, we can use a strain gauge to measure the displacement. Then I have strain gauge type pressure sensors. We can use an LVDT for the measurement of displacement. Then we have LVDT type pressure sensor. We can use variation in capacitance as the plate moves. Then we have the capacitance variable capacitance type pressure sensors. Variable reluctance we have already seen, where the reluctance of the two coils are varied. It's also possible to put piezoelectric material to check the displacement of the pressure sensor. So we have piezoelectric pressure sensor. The piezoelectric phenomena, it does not respond to DC, so constant pressure it's not, you cannot measure. In fact, there's a very nice company called Q-Light. Please, if you're interested, you can check this Q-Light pressure sensors. Then also possible to have piezo resistant pressure sensors. I talked about this when we talk about resistive displacements, resistive type of sensors. So that's about measurement of pressure. Now we come to measurement of temperature. Right? Of course, we have learned RTD. We have also learned thermocouples. Then we talked about thermistors. All these three we have already learned. Now there are other types of very popular. This one, if you have been watching the TV, you would have come across the patient's temperature being monitored by a small handheld equipment just pointed towards the head. So any material at a temperature theta emits infrared radiation, which is proportional to the theta. Of course, it's proportional to theta power 4 because it's radiation. But the problem is, if you put a sensor and look at how much IR radiation I am getting, the IR radiation here has 4 components. We call it as ABCD. Of course, A is ambience. Please remember the surrounding. If theta is, let's say, my body, 37.4 degrees centigrade, maybe I am in Chennai, so the air itself is 31 degrees centigrade. Air will give the ambience. B is called transmission. There is maybe another object. I am very close to a window. Window is getting heated up, so I will get B also coming. And C is actually proportional to theta, and D is reflectance. So this theta can go and hit some other, maybe a wall, maybe another person standing by. heat and come back. So the problem is that you should avoid A, B and D, measure only C. So one way of doing it is you put an optics, infrared optics, and put a sensor here so that you focus only on a point onto the uh, where you want to measure theta. This is what is very popular, that you see the handheld one. You will also see that there is a small laser pointer here which tells you where you are measuring. It puts a point uh, of focus that's being focused onto the. So the infrared sensing unit, cadmium sulfide, lead sulfide. There are several other materials with which you can measure infrared. Uh, this is one of the popular methods. Apart from this, there are other methods of temperature measurement, especially very high temperature and very low temperature, which I am not going to cover. Um, then we come to the uh, uh, the so we after the temperature measurement, we are going to concentrate on flow. So normally flow is fluid flow. It could be compressible fluid like water, some liquids, or it could be uncompressible fluid like water or liquids, and compressible fluid like air, gas, any gases, right? Um, there are different types of flow meters available. Um, the very popular one is called the orifice type flow meter. So you have flow in a pipe, you just put a disc with a hole. So this is just disc with a hole. So when the fluid flows like this, it so if there is a P1 here and there is a velocity V1, this will be P2 V2. So it is the same. So if you derive, then the flow rate Q is CD A2, where A2 is the area here, by 1 minus beta power 4 square root. It's all really complicated formula, but 2G by mu into P1 minus P2. We see that the flow rate is proportional to P1 and P2, and the proportionality is square root. So this will be a nonlinear flow meter. So you measure P1 minus P2 minus P1, you get. Uh, Instead of just putting an orifice, you can also put a venturi type of flow meter, where the same thing, but you gradually decrease the area available for the fluid to flow. Then you have the venturi flow meter, somewhat similar to the same as right? So you make it like this. So again, you have P1, you have P2 here. It's the same. Uh, the formula is slightly different, but it doesn't really uh, that big a problem. Then we have what is known as PTOT type of flow meter. So we have a pipe here. So the fluid is flowing with a velocity v. You just put a pipe like this. So we get P2 here, and this we call it as total pressure. This is wall static pressure. Then velocity v can be derived as square root of 2g by nu is a specific weight into P2 minus P1, or P total minus P wall, right? P total minus P wall. So this is again a flow meter, but the problem is you have only the velocity at this point is measured. So sometimes people use several openings here, right? So you get V1, V2, V3. So then you call this as averaging P dot type flow meter. The next is the rotameter. So you have something like this. So you have, and you put a plunger, and so the distance of the plunger is proportional to the flow meter. So here again there's a complicated formula. This is not an electronic type flow meter, even though we can put a sensor for this displacement and make electronics. I'm just including it so that you understand there are different types of flow meters. Then you have turbine type flow meters. So again what you do is you put a turbine, and any velocity again rotates the turbine, and the speed of the turbine omega is proportional to velocity. This is very popular in measurement of very low velocity flow, especially in 5 flow. For example, if you buy water meters, the amount of water that is being supplied to your house, uh, basically it will be turbine type flow meter, right? Um, the one problem is that the water has to flow fully in the type. If water flows only half, which is true for most of our houses, then this will not work. However, what you can do is, in such cases, you make the flow itself like this. So you have water flowing here, water flowing here. Even if it's flowing only half the tube, here it will be full tube. So then you can put the turbine here and measure the velocity. So the problem of half pipe flow can be very easily taken care of, right? Here the formula is very the flow rate, volume flow rate is TPF by NP. This is a very popular one. The other one is the ultrasonic or Doppler type of flow meter. You have a 5 flow, you put an ultrasonic transmitter here, and you have an ultrasonic receiver here, you have the velocity. So if I send at a frequency f, I will get f plus delta f, not minus delta f, right? It's only for the direction of velocity, it will be only plus delta f, and delta f is proportional to velocity. This is not very popular because this needs a very quiet, calm atmosphere. The other one is the electromagnetic flow meter, used for only conductive fluid. So what we do is we keep the pipe, insulating pipe, and then we put two contacts, electrical contacts. Take this and put magnet north south and the flux. Now this can be so I have a flux density B, I have a moving conductor at a velocity v, so I will get an induced EMF E equal to B L into V, right? So B is constant, L is constant, V is constant. Again, this is rather very rudimentary principle of operation. The actual electromagnetic flow meters are quite complex, and we don't use a permanent magnet. Instead, we use an electromagnet so that we can control B and hence measure the velocity. Um, with this, we come to the end of the transducers course. Uh, I don't know what is going to happen in terms of the examination. I'm just waiting for the situation to clear. Once the policy decision is given for the examination, I will contact each and every one of you about the exam and how it will be conducted. Keep safe, stay at home, do not venture out without a mask, and see you soon. Bye.